Excellent. Lecture number 37, announcements. Homework 9 is due today. Wow, that kind of puts a downer on things. Please work on homework 9. It's one of the longer ones. It's worth 4 points because we combined homework 9 and homework 10 into one super big homework, so we wouldn't have the deadline for homework and the deadline for the project at the same time. But now you pay the price by having an extra long homework due today. Quiz 4 is due tomorrow. The lab's due today, that's true. Friday's special, in that I won't make videos, so you gotta come to class. Tell your friends. At the last 15 minutes or so of the lecture, you'll get a paper survey administered by HKN where they'll ask you about how the course went. And if at least 60% of people respond to that survey, everyone gets an extra credit point. Okay, Friday's also the last lecture, then the course is over, but there's still a final exam. Next week, we will have 18 hours of review sessions, in case you want to review. That will be held Monday, Tuesday, and Wednesday from 11 to 5 in 271 and 273 Soda. They will have topic-specific agendas, so you'll get to look at the topics, which will be posted online on Piazza over the weekend, and decide which things you want to learn about. Now, something I would suggest if you are worrying about how to prepare for the final exam is that you should take a practice exam early. If you take a practice exam the day before the real exam, it's not as helpful as if you take it, for instance, now, and then you know which topics you should review. So in every one of these review sessions, there will be 2 TAs available in 2 different rooms. One room will be review session going over topic-specific problems in more of like a lecture plus you do some of the project problems yourself format. And then the other room is unrestricted. So if you want to come in at a time that isn't according to the topic on the schedule and just ask whatever question you want to ask, you can certainly do that on Monday, Tuesday, and Wednesday of next week. It's kind of always something different. So we'll just march through the course from beginning to end. If you want to camp out for 18 hours, you're welcome to do that. Most people kind of pick and choose what they want to learn. Oh, will some of the practice problems be posted? Yeah, definitely. So if you want to study on your own, we'll give you some materials. Okay. So, occasionally people ask me what I do for research. I work on something called natural language processing, which is how we get computers to do something useful with natural languages, like English or Chinese. It turns out you've learned enough in this course that you can actually make progress on that kind of problem. So I thought I'd just take a day, show you an example of the kinds of things we build, and show you how some of the ideas that you've come across in this course apply. So we're going to work on a problem called natural language parsing, which takes in a sentence and tries to figure out the structure of that sentence. Now, you've probably noticed as you built your scheme interpreter that computers are perfectly good at interpreting programming languages. They just apply the rules of the language, and out comes the value for every expression that you want to evaluate. Interpreting natural languages is harder because of ambiguity. So there are multiple reasonable interpretations for the same sentence. That doesn't happen in programming languages, but it does happen in natural languages. So here is a sentence: programs must be written for people to read. This comes from the textbook Structure and Interpretation of Computer Programs, also the name of this course. And the idea here is that you should write your program so that someone else could read them. So even in this simple sentence, we can start to think about what structure it has. So the whole thing's a sentence, and it contains a noun phrase, which is the subject, programs, and it contains a verb phrase, which is the whole predicate, about programs, that they must be written for people to read. And within this sentence, there's another sentence called a subordinate clause, which has its own subject, people, its own verb, the people are reading. And it's subordinate because it's describing something about how the program should be written. So the structure of this sentence basically says that programs must be written in a particular way. That particular way is for people to be able to read them. Okay? Now, it turns out this is not the only structural interpretation of this sentence that we could imagine in the English language. Instead, we could consider a structure that looks like this. Programs must be written, and here I've brought for people to read out of the verb phrase, modifying the whole sentence. This would mean something like, in order for people to read at all, like for anyone to be literate, programs must be written. Now, that's not really true. I mean, people read before there were any programs. But just because it's false doesn't mean it's not a reasonable interpretation of the sentence. So this is a different structure for the same sentence. Here's another one. Programs must be written for people in order for those programs to read. Okay, so this says to, oh, sorry, it went too far. This says to read is some verb phrase that's describing something about programs. Now, programs don't really read, and this makes no sense again. Well, it does make structural sense. It's a reasonable interpretation. It's just a sentence that happens to be false. Okay, so the goal for today is to write a program that will take in the sentence and tell us which structured interpretation is reasonable given that sequence of words. So how does it break up into noun phrases and verb phrases, and which verb phrases are part of other verb phrases, etc. And there's a related problem we're going to try to solve at the same time, which is that for every word, I should say what kind of word it is. So there are lexical categories in a language that tell us how one word can combine with another word to form a phrase. And some of those lexical categories are like nouns or verbs, and program could be a noun or a verb. So here's a series of coded software instructions is the definition of the noun, and the verb would be to provide a computer with coded instructions. So you now know how to program. And must can be a noun or a verb as well. I must do something, or it's musty in here. Why is this house full of must? Dampness or mold. So it's obvious to you, in this case, that must is the verb, because you speak English. But it's not obvious to the computer unless it has some mechanism to consider different possible interpretations of the sentence and figure out which ones make sense in the context of all the other words. Okay, so we're going to try to do two things. For every word, we'll try to figure out its lexical category in the context of a sentence, and we'll figure out how those words combine into phrases and the structures of those combinations. And that's called parsing a sentence. Questions so far? Okay, how do we do it? It's going to be a long road, so bear with me. If you have questions, ask them along the way. We're going to build up some machinery first, and then we'll have a system that actually works by the end. First, we need a way to represent the trees that we're trying to generate. So those are called syntax trees. And you know all about trees from this course. We represent syntactic structure using something that has branches, and those have branches, and those have branches, and in the leaves of the tree are the words. So here's a word, cows. Cows is a noun. There are some cows. Those are some mighty ugly cows. Okay, now if we're going to write a sentence about cows, we need to say what they're doing. Those cows are looking pretty tough. They're doing what cows typically do, which is to intimidate. Are you intimidated? I suspect you are. Intimidate is a verb. Now, what do cows intimidate? Mostly other cows. Okay, so here are some cows intimidating some other cows. And this sentence while quite short, does have some structure. So this whole thing is a sentence which has a noun phrase, which has a single word, noun, cows, and then the verb phrase is intimidate cows, which has a noun phrase within it. With me so far? Okay. Now we need to represent all this in code. So here's how we're going to do it. We're going to have a class called tree. Tree will have two different instance attributes. The tag of the tree is like the root symbol. So is it a sentence, or is it a noun phrase, or is it a verb phrase? And we'll just use these abbreviations S and NP and VP for sentence, noun phrase, and verb phrase. And then each tree has a sequence of branches, a list of branches that tell it what are the constituents of that tree. The sentence is made up of the noun phrase and the verb phrase. And then we're going to have a separate class for leaves. And the reason we'll have a separate class is that we want to keep track of individual words. So a leaf has a tag that tells us whether it's a noun or a verb, and it has the word itself, cows or intimidate. So if I want to actually use code to represent this sentence, I'll say so before I do that, I'll go through all the pieces. So there's a leaf, noun cows, there's a tree, noun phrase has one branch, that branch contains the leaf. There's another leaf, there's another leaf, there's another tree. Here's a tree where the tag is verb phrase and it has two different branches, a leaf branch and a tree branch, and this tree has one branch, the leaf branch. And this whole thing is a two-branch tree. So here's the code. I need cows, which is a leaf, which is a noun, cows. Intimidate is a verb, intimidate. S, NP, and VP, I'll just use the strings S, NP, and VP. Keep my life simple. And then when I want to define an instance, a tree, that represents this whole sentence, I'll say it's a sentence which has a noun phrase, which has a branch cows, where cows is a leaf. And it also has a second branch, which is a verb phrase, which itself has two branches, intimidate, and then a noun phrase containing cows. So this hierarchical structure is now expressed in the Python language. Okay, stop for a second. How are we doing? Yeah, so far we've just hard-coded what's a noun and what's a verb. In the end, we'll try to learn it automatically. But we've got to understand the machinery first. Okay, keep trying to think of questions while I show you a demo. Here's the code. There's a class called tree, which has a tag and some branches and remembers the tag and the branches. There's another class called leaf, which has a tag and a word, and it remembers the tag and the word. Here's cows. Here's intimidate. And here's the whole tree. So if I load this file, then S is some tree object. Its tag is S, it's a sentence. If I look at its branches, they have noun phrase and verb phrase as their tags. And so we can explore the whole tree like this, piece by piece. I also have a little helper file called printtree.py. And what printtree does is it prints out the whole tree. So I define the tree here as cows intimidate cows, and I print it out, and it says cows intimidate cows. But it gives you the structure. It says the sentence made up of a noun phrase and a verb phrase, and the noun phrase has a noun, and the verb phrase has a verb and a noun phrase. So this is just a little recursive function that says, if it's a leaf, print it out. Otherwise, it's a tree. So we print it out, and we print out all the branches. I won't go through the details. But any questions so far? Okay, so we can represent trees. That's something. Now we want to be able to generate trees. In fact, it would be nice if we could generate all trees. So here's how it goes. There's another structure called a grammar. And a grammar is a collection of rules about how you can build up sentences from components. And there's a particular kind of grammar called a context-free grammar. This was invented in linguistics, but turned out to have massive applications all over computer science. So now mostly it's computer scientists that study these things called context-free grammars, even though they were originally applied to language. Okay, so a context-free grammar rule describes how you can take one tag, such as S, and expand it into a sequence of tags, such as a noun phrase followed by a verb phrase. So I might write a context-free grammar rule like this. This says, if I have a sentence, one way to expand it is as a noun phrase followed by a verb phrase. So this thing is called a context-free grammar rule, and a whole grammar has a bunch of rules. You can have as many as you want. I could say the way I expand a sentence is as a noun phrase and a verb phrase, the subject and the predicate. Once I've done that, I have to know how to expand the noun phrase. So one thing I can do is have a noun phrase that's just a single noun, and that noun could be cows. What about the verb? Oh, there's some cows. Okay. So what about the verb phrase? Well, we need a rule that can expand the verb phrase. Otherwise, we're stuck. So the verb phrase can be expanded as a verb and then a noun phrase. Now, we already have a rule that says how to expand a noun phrase. But we need a rule that expands the verb. So the verb could be intimidate, and then the noun phrase could be a noun. Oh, that just intimidated me. Did you see that? That was awesome. I forgot I put that in the slides. Okay, so we got some angry cows. And what are they intimidating? Well, of course, the other cows. Okay, so what you should understand at this point is that I could come up with a description of how language works. Now, this is a simplified description. We don't really know exactly how language works or how people acquire it. But we can hypothesize that this is one mechanism for generating lots and lots of sentences. And then we can see how it performs. Does it generate real sentences or not? So the way we're going to describe a bunch of sentences is by writing down grammar rules and then using them to expand sentences into noun phrases and noun phrases into nouns and nouns into cows. Questions? Okay. We're about to write a bunch of code. So there's something conceptual. Okay, we'll go write the code. Here we go. So, we know there's a tree class and a leaf class. What we'd like now is to be able to express trees using a grammar. And so here's a new file that contains the grammar. Now, I said there's just a bunch of rules, but in this case, to simplify the code, I've split them up into two different categories. There's the lexicon. The lexicon has all the leaves. That there's a noun cows and there's a verb intimidate. And then there's a grammar, and the grammar says, for each symbol that's not a leaf, here's all the ways of expanding it. So an S can be an NP-VP, a noun phrase can be a noun, and a verb phrase can be a verb followed by a noun phrase. What I'm going to do now is write two functions that take in symbols and expand them into whole trees. Okay, so what does expand do? Well, it's supposed to yield all the different trees that I could get for a given tag. So tags are like N or V or S or NP or VP. So if it's the case that this thing is in the lexicon, I want to just yield the leaf. So I'm going to go through all the different leaves in the lexicon. If it turns out that the tag of the leaf, N here, matches the tag that I passed in to expand, then I'll yield that leaf. So this handles applying the lexicon. And what about the stuff that's not in the lexicon? Well, if the tag is in the grammar, meaning it's S or NP or VP, then I'm going to go through all of the different ways of expanding that tag. Grammar is just a dictionary. I look up the tag. I get the sequence of all expansions for every one of those. I'm going to expand all the tags in that tag sequence by calling expand all. Once I've expanded all, I'm supposed to yield a tree. So I've yielded individual leaves, but if I want a larger tree structure, then I have to build it by instantiating the tree class, using the tag as the root symbol, and then the branches as all the branches. Okay, so this says go through all the ways of expanding the symbol, and then recursively expand all the tags. So what's expand tags do? Well, that takes in a sequence of tags. So for instance, V followed by NP. If it's the case that the length of that tag sequence is just 1, well, then that's a pretty boring case. It's really just that we need to expand that one tag. So I can get some branch by expanding that tag. Now that tag is the element at index 0, but the length is 1, so it's really the only tag that's in there. And then I'm going to yield it, but instead of just yielding the branch, I'll yield a list containing that branch, because I'm supposed to yield a whole sequence. So this says if one tag comes in a list, one branch comes out in a list. Otherwise, there's more than one tag here. So now we have NP followed by VP, or V followed by NP. What I'm going to do is break those up into the first and the rest. So I get tag 0, I get tags 1, etc. So this goes from tag 1 all the way to the end. And then I just get all the branches that I could get by expanding the first tag, all the branches that I get by expanding the rest of the tags, and put them together into a big list. Okay, so I left a little blank in here. Maybe you can help me out. I used expand to expand a single tag. Rest is a sequence of tags. How would I expand that? Oh, I could call expand all. Good idea. So these are two mutually recursive functions. Expand calls expand all calls expand. It also calls expand down here, and by the way, it also calls expand all. Okay, I'm done. What have I done? Well, okay, so then at the end it says, for every tree that you get by expanding the sentence symbol, print it out. Okay, so Python 3 x.py should expand s into every possible way, expand that into every possible way, expand, expand, expand until you get words, and those words are cows intimidate cows. Let me pause. Yeah, so the only way so far, according to my lexicon and grammar, to take an S and get all the way down to some words is this sentence. Question? So if we added more nouns, would we have way more sentences? Because we could combine any noun with any other noun, and we'll just get this huge long list. Yeah, that's exactly how language works. So the question is, why are we yielding everywhere instead of returning? In this case, where we only really have one structure, it doesn't matter. But the idea of using yield is that there might be multiple different trees that we could build. So let's try that out. Let's expand our grammar a little bit to have one more word. So what do you call someone from New England? I call him a Yankee. A Yankee is an adjective. Okay, and this says a noun phrase could be a noun, or it could be an adjective followed by a noun. So a Yankee cows would be cows from New England. Now, if we run this, we see that there are actually 4 different sentences. Cows intimidate cows. Cows intimidate the poor Yankee cows. The Yankee cows are now really tough, and so they intimidate cows. And then we have Yankee cows intimidate Yankee cows, which is this regional conflict in New England. Now, without the yields, this wouldn't happen. If all we did was return each time, then we'd get only one, the first thing that we found. But by yielding, we're actually going through and enumerating all possibilities. And that's why we get lots of stuff. Okay, more questions? Oh, why do you put J for adjective instead of A? Turns out A is kind of overloaded in the linguistic vocabulary because there's adverbs and there's adjuncts and there's adjectives. So people don't use A's for lexical categories because it confuses people. It's just some like weird convention that natural language processing people do. I agree it's confusing. Okay. So how could we generate even more sentences? Well, it turns out you can put a sentence within a sentence. We saw this already. The log fell on my house is just one sentence, but the log that I cut down fell on my house has this extra sentence within it, I cut down. And we can do the same thing here. We can introduce a relative pronoun, which is the word that. And we can say that a noun phrase could either be just a noun phrase or an adjective and then a noun, or it could have a relative clause, which we'll call an RP. So a noun phrase could be the log, or it could be the log that I cut down. Now, if I introduce this idea of a relative clause, I have to say how it expands. So that I cut down is how you would build that. Okay, so now we'll have cows intimidate Yankee cows, and we'll also have other things. How many other things? Actually, we're going to have a lot of other things. And the reason we're going to have a lot of other things is that a noun phrase can have a noun phrase in it. Well, this comma's okay. Okay, a noun phrase can have a noun phrase in it, which means a noun phrase can have a noun phrase in it. So I'm going to pipe this through less, which means instead of printing forever, it'll just print until it fills the screen. And we'll have sentences like cows intimidate cows, or cows intimidate Yankee cows, or cows intimidate cows that cows intimidate. Oh, that's rough on these cows. So these cows are intimidating these cows, and these cows are also intimidating these cows. And cows intimidate cows that Yankee cows intimidate. And then down here, oh, here's where it gets serious. Cows intimidate cows that cows intimidate. That's a sentence in English, right? So we only have a handful of words here, and we can actually generate as many sentences as we want because we can have these long chains of intimidation. Cows that intimidate cows that intimidate cows that intimidate cows. There's no limit here. It will just go forever. Literally. Okay, so with 4 words, we generated all these sentences. Well, it turns out we could do it with even fewer words than that. Those beasts that you saw on the slide, they weren't cows at all. They were buffalo. Remember them? Those are buffalo. So the plural of buffalo is buffalo. when buffalo intimidate other buffalo, there's an English word for that, about the particular way in which a buffalo intimidates another buffalo, and that word is buffalo. So buffalo can be used as a verb. So I could buffalo you, or a buffalo could buffalo another buffalo. In upstate New York, there's a city. There's a city called Buffalo. Okay. Now let's see what kind of sentences we get. So now we have buffalo, buffalo, buffalo. So cows intimidate cows. Or we have buffalo, buffalo, the Yankee buffalo. Or we have buffalo, 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 the buffalo, buffalo. Same sentence we had before. And we have buffalo, 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 that buffalo, 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 etc. So we have some pretty long sequences of buffalo. But there's this occasional that in the middle. Well, it turns out in English, the that is optional. I could say, the log fell on my house. I could say, the log that I cut down fell on my house. Or I could drop the that, and I could say, the log I cut down fell on my house. And similarly, I could say, cows intimidate cows. Or buffalo, 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 buffalo. So the way I'd write that down in my grammar is just to say that a relative phrase doesn't need the relative pronoun at all. It's just a noun phrase followed by a verb. Okay, so now we have a grammar that can generate an arbitrarily long sequence of buffalo along with its grammatical structure. But that's not quite the problem we set out for solving. So far we have something that can generate a bunch of sentences. But what we wanted was to take one sentence and come up with its grammatical structure. And that's called parsing. It turns out it's very similar to what we've done so far. So here's how you parse something. You expand all tags recursively, just like I showed you, but you make sure that the tree you build has the right number of words, and those words match up with the ones you passed in. So if I pass in buffalo, 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 parsing it means coming up with a structure that has exactly those leaves. So I say, oh, I could have a sentence, and that sentence starts at the beginning of the sentence and ends at the end of the sentence. And in order to keep track of where I am, I'm going to come up with indices that tell me where I'm starting and where I'm ending for each phrase. So an S that spans all the way from 0 to 4 could be expanded into a noun phrase and a verb phrase, but I have to pick where the noun phrase stops and the verb phrase begins. So if I pick a middle point, 1, that means the noun phrase goes from 0 to 1, the verb phrase goes from 1 to 4, and that means buffalo is the subject, and buffalo, buffalo, buffalo is the verb. Now I can recursively apply this process, and when I do, I'll find that there's a noun. But I'll apply a constraint. So I'm going to generate all sentences with the constraint that when I reach an individual word, it has to be the word that I want to parse. So a leaf must match the input word. And that's the only thing I need to change relative to the program that generated all sentences. Now we're going to generate all sentences that match the words that came in. And that just involves some recursion, and it will come up with a verb phrase. This is just a sketch. I'll write you the code in a minute. Questions? Okay. So it turns out that we can't just pick the middle point out of thin air. We have to try them all and see which ones work and which ones don't. So I'll get a different grammatical structure if I pick a different middle point. Here we have the Yankee cows intimidating the cows by picking a middle point that says the noun phrase goes all the way to position 2, and the verb phrase goes from 2 to 4. And when I recursively call this, I get the Yankee cows intimidate the cows. Okay, keep that picture in your mind. Here's how the code changes in order to make that happen. I still have a lexicon. I still have a grammar. I actually still have expand and expand all. But what I really want to do is parse a line. The line's going to contain all the words. Buffalo, 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 the log I cut down, whatever. So we'll break those words up by splitting on space. So now I have a sequence of words. And then I'm going to expand but now when I expand a tag, I'll remember the starting position and the ending position. If it's the case that the end minus start equals 1, well then there's a particular word I'm trying to match. Because that span is only 1 long, I must be putting leaves over that span. So I get the word at index start, and I still go through all the leaves in my lexicon. I check to make sure the tags match, and I check to make sure that the words match. Then I can yield the leaf. Otherwise, I go through every rule in my grammar. I still go through every branches and expand all, but I want to constrain that to being over a span from the start to the end, which are just integers, like 0 to 4. Okay? Now, expand all needs to remember where it is, so it also has a start and an end. How do I use that start and that end? Well, if there's only one tag, like I had before, then that tag goes all the way from the start to the end. Simple enough. Otherwise, if there's more than one tag, then I need to figure out where the first ends and the rest begins. And so I say for every middle point in the range from start plus 1, which is after the start, all the way up to n plus 1 minus ln of rest. Okay, so what's that magic? That basically says everything in the rest is going to take at least one word. So the first has to stop at a position where there's room for the rest. Oh, did I mean minus? Yeah, sure I did. And I go through the first branch, and where the first branch goes is it starts at the start, but then it only goes up to the middle. And what about the rest? Well, the rest starts at the middle and goes to the end. We'll just have to live with that. Okay, and then I put the first branches and the rest branches together, and I'm done. Except for that, when I call parse, I break up the line into words, and then I don't want to just expand S, but I want to expand S over the entire sentence. So starting at 0 and going up to the length of words. Okay, so what happens now? I start up my program, and when I parse, I have to say what I'm parsing, buffalo, buffalo, buffalo. Now remember, I have a grammar that could generate an infinite number of things, but it only gives me the one that has exactly these 3 words in it. But if instead I said buffalo times 4, I'd get 2 different options. The cows intimidate the Yankee cows, and the Yankee cows intimidate the cows. So these are 2 different structures that I could put over the same sequence of 4 words. Where this little thing just says buffalo, 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 buffalo. Okay, we now wrote a parser. No doubt. Takes in some words, gives you all of the reasonable syntactic structures. As long as those words are buffalo. Any questions? That's a tricky one. Okay, talk to the person next to you. How many different trees will I get if I say buffalo, 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 given there could be a noun, a verb, or an adjective? Go. All right, let's see if we can figure this out. Does anyone have one structure for buffalo, 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 buffalo? Yeah? Or did you not raise your hand? Yeah, okay, that's one. Yeah? We have Yankee cows intimidating the Yankee cows. We have the cows that cows intimidate other cows. And maybe there's one more. There's actually three. So this is the cows intimidate cows that cows intimidate. So everyone's picking on these buffalo. This is the Yankee buffalo intimidating the Yankee buffalo. And then this is the tragic cycle of life buffalo, where you have buffalo that are intimidating. Okay, so the buffalo that other buffalo intimidate other buffalo. So if you got bullied when you're a kid, maybe you pick on some other buffalo. What are we going to do about that? Okay. So that's really sad, and it gets even more sad when you have 10 buffalo in a row, and there's just this huge number of possible parses. Okay. So that's our parser. What we'd like to avoid is having to, well, okay, so what do we do at this point? People discovered this kind of algorithm long ago, and then they thought, all we have to do is write down all the rules in the English language. And some researchers tried doing that. And professors, grew really long beards and felt overworked. And then some very clever people realized there is a better way. Instead of writing down all of the rules, they got undergraduates to do that for them. So at the University of Pennsylvania, they undertook a multi-year project that involved lots of undergraduates. But instead of writing down all the rules of the language, they actually looked at examples. Oh, don't mess with me. Okay, so what you're looking at now is an excerpt of what's called the Penn Tree Bank. It's a bunch of sentences from the Wall Street Journal where undergraduates went through and wrote down what their structure was. So the sentences in an October review of The Misanthrope at Chicago's Goodman Theater, revitalized classics take the stage in the Windy City. Okay, so that basically, we haven't even gotten to the subject yet, by the way. This is just like a long-winded Wall Street Journal sentence. And then it finally says the role of Selamine. Actually, I don't know how to pronounce that. Blah, blah, blah. Okay, so, but here you see exactly what we've been talking about. Sentences. This is a locative prepositional phrase that tells you where something happened. And in that prepositional phrase, you have to have the object of the preposition, which is a review. Okay. And there's not just one sentence, there's many. Rolls-Royce Motor Cars, Inc. said it expects its U.S. sales to remain steady at about 1,200 cars in 1990. So this is the kind of stuff that gets described in the Wall Street Journal. And then we went through and we saw exactly what we expected, that a sentence contains another sentence contains another sentence. That's how English works. Yeah, so the sentence, Rolls-Royce said it expects that something will happen. Something will happen is a sentence that's inside it expects that something will happen, which is inside Rolls-Royce said that it expects that something will happen. So that's the recursive structure of a natural language. Okay, so what we do next is instead of trying to write down all the rules, we just take all the rules that actually appear in a sentence that we observed in the Wall Street Journal. So we take the rule that there's one kind of plural noun called sales, and we add that to our lexicon. And then we also add to our lexicon that a verb phrase can be a verb, VBD means a past tense verb, followed by a sentence. S bar is this relative clause thing. So you could say, Rolls-Royce said that, it expects, or the that is missing in this case, and so they've marked that in the analysis. So you look at everything that actually showed up in the Wall Street Journal, and you count it up. Now, why do you count it up? Well, you count it up to figure out, among all the possible analyses of a sentence, which one's right. So here's a new example. What we'd like to observe is that by using counts of how often some rule appeared in the corpus, we can figure out which syntactic analysis is more common. Teacher strikes idle kids. So this headline is about some teachers expressing their collective bargaining rights, so they went on strike, and that left some kids idle in the classroom. So sad. So that's a sentence that has a noun phrase, the teacher strikes, and then a verb phrase, which has the verb idle, and then the kids as the noun. And if we look in our corpus in the Wall Street Journal, we can see how often each of these different expansion rules actually appears. So what I'm going to show you is the rule frequency for every 100,000 tags. So for every 100,000 S's, there are 25,000 that look like a noun phrase followed by a verb phrase. That's the most common thing. You have a sentence, which is the subject, and then the predicate. Now, there's lots of different kinds of noun phrases. Having two nouns in a row, one singular, one plural, happens 1,300 out of every 100,000 times, and etc. And we can come up with these counts for leaves as well. So this says for every time we see a noun in the Wall Street Journal, 5 out of 100,000 of those are the word teacher. Every time we see a plural noun, strikes is about 25 out of 100,000. And idle gets used as a verb, and kids gets used as a plural noun. And if we multiply all these frequencies together, we get some estimate of how likely it is that this sentence would appear with this structure. Now, it turns out there's a second structure, a second analysis, which is that there's some teacher that strikes the idle children, something I completely respect. Do not be idle. Okay, so this actually uses different rules. Now we have the noun phrase coming out as the noun, which means it has a higher count. But the way the verb phrase is expanded has a lower count. And the way that we used an adjective here has a lower count than when idle was a verb. So we can multiply all these together and see what we got. And that's basically how a parser chooses among different analyses. Okay, I'm not going to write all the code for you because we're out of time, but I will show you the difference between the thing that we wrote and the program that actually parses using all of this stuff from the undergraduates. And the answer is, it's basically the same. So instead of writing down a grammar by hand, we load it up from some file. And then we expand all of the things, but we also score them. So there's some memoization, and then there's some check and multiply together all the frequencies and see what comes out. But basically the same algorithm is running on the left and the right, but we need a little bit of extra infrastructure to make it work with scores. Okay, this is all posted online, so I'm not going to go through it. I will show you how it works. If I run max parses, oh, don't give me no lip. Max parse, there we go. Then I can parse teacher strikes idle kids. And it's going to try all the different structures that it could possibly find and come up with these two. This is actually just the program we wrote with a little bit of additions, and it gets exactly the two analyses that we talked about. The teacher strikes, idle the children, or the mean teacher strikes the kids that deserve it. Okay, and that's natural language parsing. I'll see you on Friday.